Hi there, welcome back. When I left off last time, we just checked that we have reception on all channels, which is great news. And I was left with completing the checking of components, swapping out resistors and so on the radio section. Because from the power amp onwards, the AF section, that was all done. So that's what I got down to doing. And what you'll notice, well, you might notice, there's no yellow fever here. I used a Vima cap over there and a Mallory over here because these are the components that I had on hand and ran out of some of the yellow ones, but the values are right. Other than that, all components checked out fine. Resistors were fine. The coils were showing continuity. And everything else has been checked and completed. There were two capacitors over here. That one over there is a new one, as are those two over there. So what we have now is the radio section, at least the AM side, complete. And here's the result of that work. Most of this has been painted in, it's been checked, and anything that needed replacing has been replaced. As I said, only a couple of, or 3-4 caps were done. The rest seem to be fine. All resistors seem to be fine. And having tested afterwards, the radio is still fine. So the next obvious step is the IF alignment. I'm going to do the IF alignment on the AM. Now this radio has a rather, I suppose you'd call it unusual, IF frequency. It's 468 kilohertz. And what we're going to use to complete the alignment is the information that they provide. And here it is. This gives us a layout of where the various IF transformers are. So there's one back there, there is 2, there is 3, 4 and 5. So there are 5 IF transformers, and we just need to check which corresponds to which. So some of them will be for the AM, some of them will be for the FM. And to start off with, we're going to ignore the FM completely. In fact, we're going to be careful not to touch it and just work with the AM section. And what they tell you to do here, I have the German instructions here, and they basically tell you what is quite standard. You put it on an AM channel. Usually we put it on a medium wave. Here they ask us to put it on a short wave. And then you feed a signal into the grid of the EBF89 and adjust the 3 final transformers, or rather coils. 2 IF transformers. One of them has got 2 coils, the other one's got 1 coil. And then you move your signal to the grid of the mixer IF amplifier, the ECH81, and you adjust the 2 coils of the IF transformer closest to it. Pretty standard. They give you a few more details like sensitivities, but not too worried about that. They do suggest something that is not quite new to me, but I've finally understood what this means. What they say you should do is that when you adjust one transformer, which has a primary and a secondary, you dampen the coil opposite the one you're adjusting. So if you're adjusting the primary, you connect a 10K resistor and a 5 nanofarad capacitor in series across the 2 windings of the opposite coils. So you dampen it. If you're adjusting the primary, you dampen the secondary. If you're adjusting the secondary, you dampen the primary. Now the reason for this, and I found a translation of one of these repair helper sheets from Grundig. It's a completely different model, but I found one which had been translated into English, which is great help. And they say that the reason for that is so that you reduce basically any effects of the second coil. The second coil could actually affect the sensitivity of the first one, so you can actually create a sharper adjustment. Now, I'm not too worried about that. I could do that. I've actually got one of those little damping coils done up. All I did was I connected a capacitor and a resistor in series, and I connected it to 2 crocodile clips, and we could use that, but I don't really think it's necessary. I suppose if you were using very big signals, you could have a problem, but we're using very low value signals here, and I don't see that that will be necessary here. So I'm going to set things up. I'm going to set the signal generator to the frequency, connect it up, and show you where we are. So I've got the signal generator connected at set at 468 kilohertz. The amplitude is the absolute minimum that I can get on this one. The modulation is 30% AM modulation, and I'm going to activate that. Because that signal is still significantly higher than I need, I send it through this DIY AC coupled attenuator, and it allows me to do 6, 12, 18 dB separate switches. In this case, I'm going to put it to a full 30 dB, just add them up, attenuation, so I have the smallest signal possible, and I need to keep this as low as possible so that the AGC doesn't kick in, the automatic gain control. We want the signals to be as small as possible, as long as they are discernible as audio signals, and we tune it at the lowest possible signal. I then have a dummy load connected to the speaker terminals. This is exactly 5.6 ohms, which is what the radio calls for, and across that I have my AC voltmeter across the dummy load. So we're going to actually measure the audio response, audio result of the of that carrier, that IF frequency carrier with the modulated signal on top. Now, from the schematic, we know that coil number 1 is related to the FM, so we leave that alone. Transformer 2 has 2 sets in here, and the one we're interested in is the one with no Roman numerals, so 4 and 5. So it's the outer one, the one closest to the edge. That is one of our IF transformers. And over here we have the 2 inner ones, F3 and F4, that are related to the AM. So we have to adjust F3, which has coil number 1 and 2, and F4, which is coil number 3. We leave this one well enough alone completely. We don't touch that. So knowing where we're going to play with, we know that we are dealing with the outer one here and the 2 inner ones there. Coil number 3, for example, has one that you get to through the top and one that you get through the underside. Coil number 4 has one which you can get to through the underside. Yep. And then this one here, which is the one close to the edge, also has 2 coils, 2 cores, and both of them are, one of them's from the top, one from the bottom. So that's what we're going to be doing, is adjusting those cores. Now, the first thing to do is, let me show you the cores. This is the double IF transformer, and that's the core that you're looking at right in the center. That's the underside one. There's a corresponding one at the top, and if we move across here, we are going to be adjusting the 2 IF transformers at the back there, at the top there, and the 2 underside cores are visible, if you can see that, and then there's one core on the top of one of them. Now, what I had to do before going any further, and you'll notice here there's a lot of wax in there. So this is the IF transformer for the FM, which I haven't touched yet, and you have to clear that wax away very carefully so you can get to the cores and be able to adjust them. So the first thing you do is you clean out the wax carefully, and then you're ready to start. Now I'm going to set this up on the voltmeter, the AC voltmeter, and I'll be adjusting the cores, telling you which ones I'm doing, but I won't be moving the camera backwards and forwards. It's pretty simple. We'll just see the result. Okay, so here we've got the voltmeter set on 3 volts, and I'm reading 1.6 or so volts AC. This is across the speaker. Remember, I've got a dummy load instead of the speaker, so we don't get bothered here with the noise. And now what I'm going to do is I'm going to start on coil number 4. So transformer 4, transformer 3, those are the 2 that are closest to the output. And let me start on coil 1. Let's see, that's underneath here. Nope, that's the other way. Let's go up. Go for a peak. That seems to be the peak over there. There's the peak. Okay. Now coil number 2. Wrong way. Okay. Oh, that's quite an improvement. Okay. Let's peak it. And that's peaked over there. Okay. Now I'm going to coil number 3. That's on the other IF, the second IF transformer. It seems to be at a peak as it is. Okay. There's a peak. Yep. Okay. Now I'm going back closer to the RF section, and I'm going to do coil number 4 and 5. Oh, that's quite a nice change. Just a bit more. There we go. And now I'm going to do coil number 5. That's on the underside. Oh, that was already at a peak. That's it. Close enough. I'm just going to go back and check the others. Just try and get a little bit more juice out of this. Try not to make it worse, which happens a lot, by the way. There we go. All right. That's how IF peaked on the AM. Fairly easy. Now I want to show you something. If you recall on some of the previous ones, restorations I've done, I've peaked the IF visually with a scope. And what we've done is we've just peaked it using the AF output. So what I'm going to do now is I'm going to set it up so we can see what kind of response we've actually got. Let me set that up and tell you what I'm doing, and let's see what the result is. Okay, I'm using this particular schematic. This is the one that's not as legible, but it's certainly drawn up a lot more logically. Now, what I do to measure the filter curve is to use the AGC or the AVC voltage. It's basically the voltage that is representative of the strength of the signal. So the AGC voltage is produced, let's see, where are we? It's produced here, that diode on that EBF80. I might be wrong, but I think that's right. So whatever voltage you have on this part here is proportional, and it's negative, proportionally negative to the strength of the carrier signal. Okay, so what we end up with here is a voltage that is used to adjust the gain of the preceding stages, the preceding tubes. So the stronger your signal, the higher that voltage negative. And if you feed that back into the grid of those curves, you make it more negative, you reduce the gain. So you make all signals try to achieve a similar volume level. But anyway, that voltage comes through there, goes through that coil, and it comes out here at that point there, which then sees two very big resistors. This first one, the bottom one here, is 2.2 meg, and that then goes across to here, and it goes to a 47 nanofarad capacitor. That's your AGC capacitor, which filters that voltage, keeps it more or less stable before it gets fed to the grids of these preceding stages. And you can see that right here, there's a line that goes straight to that grid and adds to whatever's coming from the other side. So it's affecting the gain of that tube. Now, that's one place where you can measure it, and that's where I've been measuring it before. What I've found is that it's the wrong place to measure. I had a feeling, and I've actually mentioned this, that when you measure this voltage, if you're doing it in a sweep on your scope, this capacitor causes a delay in the response of the sweep. So it's not exactly accurate, because this capacitor has a time constant which charges and discharges, and that takes some time. And time, when you're doing a sweep, is precisely one of the axes of your sweep, of your scope. So I'm going to show you what I normally do, and we've adjusted it. I'm confident that I've peaked the IFs using the audio frequency, the audio output. Now we'll see what that looks like as a curve when I put a sweep across it. The other point, so this is where the AGC starts, and it goes through that resistor, and it creates the AGC voltage. It also goes through the top resistor, which is 2.7 meg, and that comes down to the grid of the Magic Eye tube. Now that gives us a hint as to what this thing is doing. It's actually the same, basically the same voltage is being used as a reference for the Magic Eye tube to tell us how strong our signal is. So it's basically a signal strength meter, so we know that these voltages are representative of the strength of the signal. And they are negative voltages, DC. So I've been measuring over there with the effect of the capacitor. If I'd measured over here, I'd also have the same lag or delay, because there's a 33 nanofarad capacitor here as well. And what I found is that these shifts in center frequency that I've been noticing are actually not there, because I should be measuring before those resistors. So I should be measuring the actual AGC produced, as opposed to the result of it being filtered by these two capacitors. So if you measure on this side, your curve looks slightly different. But let me show you what it looks like on that side where I've been measuring it before. Now remember, our frequency, our IF frequency is 468 kilohertz. So let me show you how I set up the signal generator. There's the center frequency 468. But if I look at the sweep function, I have a start frequency of 458. So 10 kilohertz below. Let's leave it at that. 10 kilohertz below. Stop frequency, that should actually be 456. Hang on. 456 kilohertz. That's 12 kilohertz below, and 468 to 480 is 12 kilohertz above. So I have 12 kilohertz below, 12 kilohertz above the frequency we're interested in. The time I'll set to 600 milliseconds. Let's call that 1.2 seconds. You'll see why in a minute. And I'll make sure that it's linear, not logarithmic, okay? So my sweep is started, and what I'm sending is the same low voltage. I might have to up that a little bit. So we set the sweep. Now what's happening here is that there is a sync. This cable is coming from the back of the signal generator, and that's our trigger, external trigger, which sends us a signal every time that sweep starts, and we're going to use this to trigger one channel of the scope, and then we're going to use the oscilloscope to measure the AGC voltage across that capacitor that I showed you, and you'll see what kind of curve we got. So what I have here is I've got the sync, the trigger signal from the signal generator coming into channel 2. I've set my triggering to channel 2, and so there's my triggering. Now if I change the time base, every time you see an up, down, up, that's one sweep of the signal generator from 456 to 480 kilohertz. That's a sweep. And I'm sending an unmodulated carrier signal that's adjusting in frequency, okay? Now the reason I put that at 1.2 seconds is I can change the time base to 100 milliseconds per division and get one exact sweep fitting across the entire scope, because there are 6 grid units here, 6 grid units here, so if you put 100 milliseconds each, you go 1.2 seconds across the top. That's our channel B we're seeing, okay? Now channel A is actually the response curve. This is the AVC voltage, which I have inverted. So channel A is giving us a voltage which I've got inverted so that we see it better. This is actually going negative, but I've made it go positive so we can see it better. And if I change the scale, I have to adjust it. I change our voltage. There's our response curve, okay? Now what you notice right away is that it's actually a fairly uniform response curve. It looks pretty uniform, pretty symmetrical. Unfortunately, it doesn't look like it's centered at 468 kilohertz. We know that we have exactly 12 kilohertz below our center frequency. So 468, that's 12 below, and it goes to 12 above, to 480. This thing here should be centered on that center there, if it was accurately tuned. Now we know it's accurately tuned. Why are we getting that? The reason we're getting that is because our capacitor, our AVC voltage capacitor, smoothing capacitor, is creating a delay on there. Now if I take this probe and I put it to the other side of that resistor, that big resistor, first of all we've got to drop the voltage because it's a lot more, it's a lot higher. Get this down here, and that's what we got. So this, we are seeing some RF on there, and that's normal because that capacitor, that big capacitor, has the effect of removing RF as well. And we see it's actually a little bit more centered. Now, if we want to improve that, we can now focus not on the amplitude of the actual curve, but we can focus on the, remember this is 1.2 seconds for each sweep. Let me try and reduce that. Let's make this 600 milliseconds, and we need to reduce the time base to half, so 50 milliseconds per division. It's better. You see, it's actually better. It looks better now, but I can still improve it by adjusting those transformers now, and I can try and get them closer to where I want them. Let's see if we can adjust that. It's moving the wrong way. That hasn't done much. Let's try one of these here. You have to try all of them and see what their effect is. And remember, you got 600 milliseconds between each adjustment. You can't do it too fast or expect it to react immediately. It doesn't react immediately. See, I can get rid of that completely if I mess it up. Now, I've got that symmetrical, but it's slightly off center. Let me adjust this for a while and come back to you on camera. And here we have it. So you see we've got ourselves a curve which is pretty much centered on 468, very symmetrical one way and the other, and the result is that we have our AM IF, I'll say perfectly, I suppose that's a subjective term, but pretty well tuned. Okay, now this is looking at it before the filtering of the ABC capacitor, so we're seeing some RF on there, that's fine. But at least it gives us an idea of the more accurate curve centered on our center frequency of the sweep. Right, so that's our IF done for the AM. I'm going to just quickly check the RF settings. If they're fine, I'm not touching them because I'll show you why. To do your RF alignment, in other words, to adjust the frequency you're getting to the position on the dial, requires you to mess with these boys. Now, what we have here is we have some coils. Some of them are for shortwave, others for medium wave, others for long wave, oscillator coils and antenna coils. And then we've got these capacitors which also set the start frequency. In other words, adjust the frequency of the oscillator to correspond to where you want it to on the dial. Now, these guys are sealed. These guys are pretty much well waxed. I don't think they've ever been touched, and these things generally hold up very, very well. What you can get, if you find there's a consistent discrepancy with the actual frequency versus what you see on the dial, is you can actually find that it's your pointer. In other words, the pointer at the front here, that your dial pointer, that is off frequency on both ends of the dial by the same amount. So better than adjusting the start and the stop, you just move your dial pointer. Because I removed the dial cords and therefore the dial pointers, it's very likely I'll have to adjust them at least in one frequency and check with the rest of the frequencies. It's a lot easier to move your dial pointer than to adjust these things. You can mess them up pretty badly, and that is not funny. Okay, so that's it for now. IF frequency on the AM done. Hopefully our reception will be just a little bit crisper, a little bit less deaf. So I think that'll be it for now, unless the RF needs some major alignment, but I don't think so. We'll check. And the next stage will be the FM alignment. All right, bye for now.